So now I think it's time for the second session for the spotlight talks. So the first one is Rita Laezza from Chalmers University of Technology, who should be there. So please, Rita, if you can go to the desk. And
you need to stop to your screen, Martina.
Yes, I'll share it. Wait.
And get the speakers here if they're here.
Yeah.
Oh.
Okay.
My name is Rita Laezza, and I'll be presenting our work on blind manipulation of deformable linear objects based on force information from environmental contacts. Deformable linear objects such as cables are found across many challenging industrial applications, most notably cable harness production. The alloys don't really oppose deformation in most directions except when being tensioned. And humans tend to use this observation to simplify the sensing and manipulation problems when handling such objects. So when we have a cable in between our hands, then we can feel the tension when we're pulling it, and we can assume that the shape in between the two grasp points is a line. And also, if we then push that cable and have some sort of obstacle, we can feel a change in tension and estimate the new shape. So it is based on this simple observation that we propose a graph representation of the object, which then is used to define 9 force-based manipulation primitives. The goal of this project is to see how far we can get with force-torque sensing alone, but I would like to point out that in any real application, vision will still play a big role, especially for handling errors. So when something unexpected happens, it's very hard to recover with force alone. So the proposed representation is summarized as a graph G and constant of the weight per unit length, which is either measured before or known, or even just measured using the motion primitives as a first step. Once we have that, then we have the path graph that is constantly updated as we manipulate the object, and it contains a set of vertices and edges. Vertices are defined in a set order, so anytime that a new vertex is added to the model, then the indices need to be updated. And also here we can see that vertex 3 was added in order to formulate this clipping motion. So when the grippers were above the fixture, then we added a new vertex to define that we want to have it clip through this object. And we can also see that each vertex contains information about the position, orientation, and also a point mass estimate of that vertex based on the rho constant. Each edge naturally contains information about the distance between 2 points, as well as a measure of the sag to evaluate how accurate this distance is. So if there's a lot of tension, there begins to have to be a bit of sag, which then means that we cannot trust our distance and we should tension more. We also have a scalar force, that is the force felt along that edge, and an estimate of the elasticity, which is needed mostly for these tensioning primitives, which can easily lead to an emergency stop triggered with the robot, and we want to try to avoid that. So the 9 motion primitives we have proposed are essentially tensioning primitives or sliding and clipping primitives. They are subdivided into coordinated control when the grippers are moving in a relative motion, or individual control when we have a single gripper manipulating the object. The most important primitives naturally are the tensioning ones, and here we demonstrated with more detail how we can see that the sag is being constantly estimated, and it shows in red when we have too high sag, and in green when sag is none, and we can assume a linear edge. We also have here a demonstration of all of the primitives on the real robot. We also tested our contact point estimation, which is necessary to update the vertices, and we see here the error decreasing as the Kalman filter observes more data, and also a sudden change that is then quickly recalculated. So we can see here how As the robot moves, the variance of the estimate becomes smaller. And then finally, we test all of this on a cable harness experiment with hard-coded primitives, which are shown here in the bottom. Thank you. My name is Rita Laezza, and I'll be presenting our work on blind manipulation.
Any questions?
Thank you, Rita.
Yeah, actually, before questions, I just want to mention, I hope that the last frame would stop there because I had to shorten the video, but a lot of the credit goes to Finn. That was the last second frame that was there. Finn did this work in his master thesis, so it was really good work.
Okay, nice.
We have one in-person question, right? Or, yeah, maybe come also just up here. I think the mic still doesn't pick it up right, so just gonna use the one here.
Yeah, so my question is, how did you estimate the slack in the rope?
We used the catenary model. Yeah, it was just a catenary model of the rope. That's why we assumed this uniform density. We need to have that estimate, and then we can actually have there's just some formulas to estimate the sag based on the tension.
Okay, great. Are there any other questions? So if not, I think we can.
That's one now.
Okay.
To execute the primitives in the last video that you showed, did you have you had all the red position holders placed at fixed spots, right?
Yeah.
So did that limit the sort of which primitives you could execute at which point of time, and how did, I guess this is the more real execution question.
Yeah, exactly. So, I mean, this is a blind operation, but we need to have some assumptions of what is around. So even though we're estimating the contact points, when you define the motion, you have to know where they are in a sense. So if you define direct motions.
Yeah, so there was no vision in any sense.
No vision at all. It was just knowledge a priori. Yeah.
We need to move on, but Rita will also have a poster later.
Yeah.
So then we'll direct the question towards her there.
Yeah.
Thank you again.
Thank you.
Thank you again.
Thanks a lot. So the next one is only Dinkel that should be there. So please, if you're there, just get closer to the laptop and I'll start playing the video.
Wires are ubiquitous deformable objects. Perceiving these objects enables robots to interact with them in challenging manipulation scenarios, like industrial wire assembly, knot untying, and autonomous human habitat caretaking. Our work on wire point cloud instant segmentation from RGBD imagery is inspired by several recent works. First, recent work automatically generates a synthetic dataset comprising single wire images where the wire masks are cheaply obtained using color-based thresholding. These images are used to train DeepLab v3+, a method of semantic segmentation to segment wires in cluttered scenes. Second, the Karayiannidis algorithm proposes the first method of RGB wire instant segmentation. The Karayiannidis algorithm enables individual wires to be distinguished from each other, building off of work produced in the auto-generated wires dataset. Third, MaskRCNN is a state-of-the-art general method for object instance segmentation in RGB images, learning to directly predict instance masks. Finally, the point-run mask prediction head is trained to iteratively predict the label for ambiguous points to refine the mask edges to finer resolutions. Point-wise semantic labeling of point cloud data remains an open challenge in computer vision. We first perform instance segmentation on RGB imagery, then apply the instance mask to the depth image. Object instance segmentation models require labeled data for training. Annotating point cloud data with object instance information is expensive. Pixel data in RGB images can be cheaply obtained using automatic labeling techniques. In general, point data in depth imagery are more difficult to label to obtain ground truth information than pixel data in RGB imagery. This work leverages automatic RGB image labeling in the UIEC wires dataset to train MaskRCNN to perform object instance segmentation, and RGB imagery. The UIUC wires training data are synthetically generated from single object images using color thresholding to automatically obtain object instance masks. It uses the copy-paste, background substitution, scale jittering, and hue jittering augmentation techniques to increase the variety of wire configurations and environmental noise classes present. UIUC wires is an RGB image dataset comprising 2,000 training images of up to 4 wires and up to 2 devices per image. Images include 2 schemes of object segmentation mask representation. With object segment semantics, or OSS mask representations, each object contour receives a unique bit mask, and occlusions by other wires and devices are not explicitly represented. With object semantics, or OS mask representations, all contours comprising an object receive one corresponding bit mask. These data are used to train MaskRCNN as implemented in Detectron-2 with the point-rim mask head. The trained model is used to predict object instance bit masks on the RGB image. Then the instance segmentation masks are applied to the image-aligned point cloud to obtain the 3D points belonging to each object in the scene. The UIUC wires work under submission found that MaskRCNN, instance segmentation, and RGB imagery performs better when wire masks are specified with OSS semantics. The proposed method of point cloud segmentation using the PR plus OSS model produces significantly more complete segmented point clouds than the PR plus OS model. Preliminary results indicate a 153% improvement in the number of points recovered using the PR plus OSS model. The segmented point cloud was used to construct an object mesh of the scene using a density-based clustering outlier removal step to smooth the scene mesh. The mesh reconstruction is a candidate 3D representation of the scene from raw RGBD data. One challenge with using UIUC wires to train instance segmentation is it does not simulate real lighting effects like object shadowing, object glare, or low light conditions. We also observe resolving self-occlusion and environmental occlusion is an open problem in wire instance segmentation. Finally, we observe point clouds are noisiest around object edges, which is a residual source of uncertainty in the scene surface reconstruction step. This work is the first to predict wire object instances in point cloud data using MaskRCNN. This work leaves the following questions for future work. Can a graph search method, such as the method used in Karayiannidis, be combined with the instance segmentation performed by MaskRCNN to improve instance segmentation performance for the class of wire instance segmentation problems? Can multiple fused sensor perspectives improve scene point cloud and mesh retrieval for the 3D wire instance segmentation problem? And how do wire detection and segmentation frameworks perform when trained on the auto-generated wires dataset compared with the UIUC wires dataset? In addressing remaining open questions, future work aims to improve the reconstruction quality for model-free deformable object perception. Thank you for your time and attention today.
Thank you, Ali. Are there any questions?
Not from the room, but maybe there's some online.
No. I actually have a curiosity. So do you think that if I understood it correctly, you now just do the segmentation using the RGB image, right?
Correct.
Yeah, okay. So have you tried also to use the depth map that you have to do the segmentation? And do you think that this may help?
So one of the motivations for this was the difficulty of labeling depth imagery, the difficulty of labeling point clouds directly, but we came up with this auto labeling technique for labeling depth imagery to train a model. Well, I don't know how obvious it is, but PointNet, there are a few depth image segmentation models that exist, but we just, because there's no sort of existing wire data set, we started from the RGB standpoint to obtain free data. Thank you.
Okay, thanks a lot. So now we have the next speaker, that is Shengyin Wang from the University of Leeds, and I think that he is online. You can just show up and I will start playing the video. Hello.
Hi. Can you see me?
Yes.
Okay.
Hello, everyone. My name is Shengyin Wang. Today, I'm going to present our work on goal condition model simplification for deformable object manipulation. This is a joint work with Matteo, Leonetti, and Mehmet Dogar at the University of Leeds and King's College London. Deformable objects are everywhere in our daily life and have a wide range of applications from housekeeping, medical operation to industrial production. Compared to rigid objects, deformable objects pose two main challenges: high-dimensional configuration space and complex dynamics, which make both planning and learning time-consuming. To simplify the deformable manipulation problem, we have conducted some research trying to fill several existing gaps. Instead of defining key features manually, such as corners and contours, we want to establish an automatic feature extraction method that is adaptive to different goals. Instead of using the expensive fine models, we want to find a simpler model with acceptable accuracy. Instead of learning high-dimensional space, we want to find a compact state representation that captures the most important and relevant information to achieve the task. This leads to the work we are doing now, namely as goal conditional model simplification for deformable object manipulation. Potential usage of the method includes simplifying the action space or state space for both motion planning and policy learning. In this work, we focused on action space simplification for manipulating ropes and clothes using cross-entropy method as a planning algorithm. Given the goal configuration, our model simplification method will find the minimum elements to approximate the original model with acceptable accuracy. Depending on the types of the deformable object, line fitting or mesh simplification will be called. After model simplification, a set of key points will be extracted as graspable points, which can reduce the searching space for CEM-based motion planning. For line fitting, we start from using two key points to approximate the original model. The position of the key points can be anywhere in the space. We use quadratic programming to find the optimal position based on our defined distance error metric. If the approximation error is below the threshold, the simplified points and line segments will be outputted. Otherwise, we will gradually increase the number of key points until the precision is satisfying. As in the example shown above, 4 or 5 points give a much simplified model with minor errors. The same idea applies to close approximation, with the only difference of using off-the-shelf mesh simplification toolkits from MeshLab. For a piece of clothes folded sideways, a simplified mesh with 6 triangles has a small enough error to approximate the original model. After model simplification, we use the simplified model to reduce our defined action space by extracting a small number of key points on the original model as graspable points instead of searching in the action space of all points. The bottom left figure shows the extracted key points in blue pentagons, while the bottom right shows the motion plan based on the simplified action space. Finally, to demonstrate the effectiveness of our proposed method, we conducted a set of comparative experiments on 4 tasks. Due to limited space, only the results of close diagonal folding are shown. As we can see from the same initial state, CEM simple, which is based on the simplified action space, can successfully achieve the task, while CEM original cannot find a feasible plan with the same number of simulation steps. Additional results can be found in the paper. Thanks for watching.
Thanks a lot. Are there any questions?
Not on site.
Okay, we don't have any remotely. I actually had just a curiosity. Do you think, actually 2 things. One is, do you think that it could be easy to extend the approach with some complex shapes, and also if you tried to apply it also in real world.
Thanks for your question. Yes, yeah, I think it can be extended to more complex shapes. But for real robotic experiments, that is still an ongoing work, and we are having still having some many problems, especially in the perception system. But the method is scalable to most complex shapes. Yeah.
Okay, great. Okay, thanks a lot.
Thank you.
If there are no other questions, I will move to the next one. There is, I'm so sorry for pronouncing it probably really bad. That is Azarakhsh Keipour from Carnegie Mellon University. That should be, no, sorry. It's Shaoxiong Zhao from University of Illinois at Urbana-Champaign. That should be there. Okay, so I'm starting the video.
Hello everyone. Today I'm going to present our work on estimation of point-based volumetric stiffness model using joint torque sensors. Estimating the stiffness of the deformed object can enable robot arm intelligently navigate around in a cluttered environment. Such cluttered environments exist in agricultural applications or our daily life. Estimating stiffness can also enable efficient autonomous packaging of the deformed object and also haptic feedback rendering in teleoperation. Existing works that model the stiffness of the deformed object either require a mesh model, which can be difficult to obtain online, or mostly work with two-dimensional planar object. Recent work modeled the volumetric obstacle distribution from contact feedback, but only recovered the geometry of rigid objects. In this work, we present volumetric stiffness field, a point-based deformed object representation that can be efficiently estimated in real time and used to predict force response during interaction between the robot and the object. We apply this method to model the stiffness of a highly heterogeneous deformed object, which is the artificial plant. Our method is as follows. First, the hardware sensors will sense the joint angles of the robot arm. Together with the geometry of the robot, the contact simulator will simulate quasi-static stick-on-stick motion during interaction. The simulated displacements of points in the field will be sent into the volumetric stiffness field, giving an expected joint torque measurements. Compared to the actual joint torque measurement, the recursive estimator will update the belief on the distribution of the stiffness in the environment. We implement an extended Kalman filter-based method that can run this update loop in 17 Hz on a normal CPU. Here, we visualize one example where the robot arm interacts with the artificial plant and the volumetric stiffness field is estimated in real time. The left figure shows the motion of the robot arm, and the right figure visualizes points with stiffness estimate greater than 1 Newton per meter. We repeatedly touch the same location on the plant from different joint angles. Here we can see two features. First, before contact happens, the free space volume is mostly estimated with low stiffness and are not visualized. There is sparse spurious estimation, but can be potentially removed in post-processing. Second, when contact happens, the estimated high stiffness region is mostly localized around the true contact position between the robot arm and the artificial plant. We make quantitative evaluation of this dataset with 11 touch sequences and 400 steps for each sequence. We take a k-fold validation approach, where we take every sequence as a testing sequence and estimate the volumetric stiffness field using the rest 10 sequences. We implement several baseline methods that directly learn this mapping from joint angles to the joint torques. The red figure shows the maximum torque prediction error per sequence, and we can see our method outperform the baseline methods by a large margin. Here, another experiment where the robot arm touching slightly different location on the artificial plant with similar configuration. Taking a zoom-in view of the touch region, we can see variation on estimate stiffness in this field. There is spurious stiffness estimation on the upper part of the robot arm because of limited number of touches and similar configurations. Estimating the stiffness by touching every location of the plant can be very tedious and time-consuming. Therefore, we implement a vision-based method to extrapolate the stiffness estimation from touch region to untouched region. We only use the RGB value and KN interpolation and demonstrate that quantitative result is interesting. We can see the branch region is estimated with higher stiffness value compared to more deformable leaves, which corresponds to our intuition. In conclusion, we present volumetric stiffness field, which is a novel deformable representation that can be estimated efficiently in real time. The estimate model can be used to predict force response and achieve better performance compared to baselines. In the future, we are interested in include correlation between motional points in the field and learn the relation to map visual information to stiffness.
Very much.
Thanks a lot. Are there any questions?
There are no questions here, but I actually have a question. Like, if I understand it correctly, you use the vision not for the estimation directly, but later for the interpolation.
Yes, that's true. We only use the vision for the
could you also use it for the estimation part, or?
That can be potentially used in the estimation, but we currently don't have that integrated in the estimation procedure.
Okay.
Yeah.
Okay, great. So I think if we don't have other questions, we could move to the next one. So thanks again.
Thank you.
And the next one now is Azarakhsh Keipour from Carnegie Mellon University. That should be there. Okay, hello. Let me start the video. Okay, let me share also.
Hey everyone, I am Mohammad Reza Musai, and I am presenting our work on detection of deformable linear objects and the physical interaction of aerial robots with these objects. Deformable objects such as cables and wires are part of many of our everyday and industrial tasks. We collectively name them deformable linear objects, or DLOs. In order to automate tasks involving DLOs, such as manipulation of cables in industrial settings, utility pole maintenance using UAVs, or stitching with surgical robots, a crucial part is to detect the DLOs in a way that the detection result can be used for further manipulation or planning. On the other hand, to extend the DLO applications to aerial robots, we need to study the requirements for physical interaction of aerial manipulators with DLOs. Some of the challenges in this application that a detection method needs to address includes partial views and occlusions, crossings, existence of multiple DLOs in the frame, and supporting different image types. Finally, the detection method needs to output a model that is suitable for other automation tasks, such as manipulation and planning. While there are many methods for segmentation of DLOs, their output as a collection of pixels is not suitable for most robotic tasks. On the other hand, various tracking methods for DLOs exists that can track the motion of a DLO across the camera frame once it is initialized in the first frame. However, as far as we know, our detection method is one of the few solutions that can fill the gap between the segmentation and tracking methods for robotics purposes. To go through our approach, first, the method segments the input frame. This output has many gaps which needs to be filled and many crossings that needs to be resolved before it can be used. In addition, the segmentation is purely a collection of image points, and we need to model the DLO in a more suitable way. The next step is thinning or skeletization, which allows an efficient extraction of contours in the next step. Each of these extracted contours are used for fitting a small DLO segment, and then all overlapping segments are removed. Finally, we iteratively find 2 DLO segments that are best fits and connect them together using a computed curve. The final output is a single DLO represented by a sequence of short fixed lengths cylinders connected to each other using a spherical joint. This output can be used as the initial state for tracking methods and had been used in our work for cable routing and manipulation. The whole process is near real optimal. The whole process is near real time. In these experiments, you can see how the detection and method can handle occlusions and crossings. To extend the physical interaction of DLOs to aerial robots, we analyze the visibility of the tasks from the end effector position perspective in simulation. We also analyzed the required forces for normal everyday manipulation tasks, such as pulling a USB cable, and concluded that even for simpler tasks such as this, the remaining wrenches to perform the tasks are barely enough. With that, I'm gonna conclude this talk, and thank you for listening.
You have a question? Yeah, just come here to the microphone.
Okay, thanks a lot.
Hey,
Are there any
great talk.
questions for?
Yes. Yeah.
Okay, cool.
Thanks for the great talk. I was wondering if you, how did you reason about which cable is on top of the other? Because in a cable manipulation, if you do not reason about that, that might bring over a bunch of problems, right?
Yes. So in this specific work, we did not reason about it. We did develop some method, and I've seen actually better methods being developed than what I just ad hoc developed. And maybe in the future work, it will be infused into this method. But right now, it does not detect which one is on top.
Would having a side view help?
Probably having a side view helps, but the methods that I've seen, I reviewed, but so I cannot disclose what methods they are. They had 99.5% success rate in detecting the top one. So I'm pretty sure it will be published.
Cool, thank you.
Thank you. I think we also have a question here in Zoom. So there is Dogar. We cannot hear you. Maybe you could just write in the chat. So he said, okay. So the question is, I was wondering how you deal with 3D DLOs.
So we started the work with 3D. Our camera was RGBD, and in the middle, this work in the perception work was done for my internship. So I did have a very limited time, and we switched from 3D to 2D, but gave a very clear guideline how 3D can be made perception. I have not worked on 3D yet. The method is very general and can be easily extended to 3D, but it's not implemented for 3D right now.
Thanks. I don't know if you hear me now.
Yes, now yes.
All right.
Okay, thanks a lot. So I
we
think
do have
now.
one more, although I think for time we might have to move to the next speaker, but I think there are a few other questions too.
Yeah, let's move to the next speaker, but just catch him.
Okay.
Thank you. So we now have the last speaker for this talk, for this session. That is Cristiana de Farias. She's online. Okay. Hi. Now I'm sharing the screen.
Today, I'm going to present our work on grasp transfer for deformable objects by functional map correspondence. The main motivation behind this work is that we want to grasp objects in an unstructured environment, such as the workshop in the image, where there are arbitrarily deformable cables, articulated tools, and rigid objects. In grasping planning literature, there are a number of methods to plan grasps for rigid objects. But what about objects that have suffered some non-rigid deformation? Intuitively, we might just think that we can ignore the object after the deformation and plan grasps directly on it after the deformation has happened. However, this can be counterproductive, as we're ignoring some previous or expert knowledge, such as task awareness, and it can be inefficient because maybe we have planned grasps before the deformation has happened and we're just throwing them away and planning them again after the deformation happened. As humans, we're capable of recognizing similar objects and similarities between objects, and we can find correspondences between different parts of a shape, even in the presence of deformation. Thinking of that, we can think of a second option, which is to transfer grasps between instances of objects that have suffered non-rigid deformation. To do that, to exploit these correspondences between parts of the objects, there's a very nice framework that was proposed in the 2012 paper Functional Maps, a flexible representation of maps between shapes, which is the functional map framework that can find correspondences between near isometric shapes, even in the presence of large deformations. And by joining that together with some user input to have some task awareness, we have our method presented in this image. We start here by selecting an object and segmenting that object in different parts. A user then chooses one of the parts of the object, and we plan a number of grasps with the Locomo grasp planner in that particular object part. Then a robot observes a deformed version of that object and gets a point cloud of the scene. It does some pre-processing to get a mesh of the object, and we then use the functional map framework to transfer the selected segmentation from the source object to the target, and we compute the transformation between those two regions. With this rigid transformation, we can transfer the grasp to that specific segmented part. And we do some local replanning to ensure that the grasp will be stable. We do a number of experiments with these 4 objects in the image here. In these different configurations, the dataset that we use is available on our GitLab page. And we have actually very nice results shown in these videos here. In the videos, the top image shows the initial grasp before the transfer, and in the bottom, we have the grasp after the transfer. And our experiments were particularly successful. We compared them with a similar method, but using CPD and ICP instead of the functional base method. And we have seen that the functional map-based method improved grasp transfer significantly, especially for objects with high deformation, such as the case of the bear, which is a more complex object, less aligned, and with a higher deformation. In this case, only our method worked and the other 2 failed. So in this work, we have shown that functional maps are a good option for transferring grasps between objects, and it allows information to be propagated as objects deform. Today, I'm going to present our work.
Thanks a lot, Cristiano. And are there any questions from the audience?
Yeah, there's one. Please come. Oh, there's two then. Just line up.
Yeah, I had a question. So is a functional map like a matrix, or like what sort of transformation is it?
So the functional maps basically works by changing the domain that we want to work from a matrix of all the vertices in the mesh to a functional basis. Like we applied Laplacian to transfer the domain, and then we do the correspondence in this Laplacian domain. So that's how it works.
Hey, do you use any environment collision information when transferring the grass to make sure it's still valid after the deformation of the object?
Yes, the way our method works is we plan a number of grasps in the beginning, and in the beginning part that we segmented, and then after we transferred, we check if the grasp is feasible. So we filter out the ones that are not.
I see. Thank you.
Okay. Thanks a lot. So I think if there are no other questions, we can close this session. And thanks again.
Thank you.
Thanks to all the speakers for being here. And now it's lunchtime.